In a previous episode, I refurbished a tattoo removal laser and built a very nice power supply for it. In this episode, let's tear down and autopsy a commercial but very sketchy tattoo laser power supply from eBay. I picked up this tattoo laser power supply really quite cheaply off eBay. It was well under $100. I can tell you right away that this thing definitely doesn't work because I hooked it up and plugged it in and it made some extraordinarily exciting noises and the blue smoke has escaped. So it looks like this is likely to be a teardown video and if possible a repair video. But let's take a look at this thing real quick. One thing to note, and I noticed when I first got this thing, is that the whole case, all of it, is plastic. There's no metal whatsoever in here, so this thing cannot be EMC compliant at all. There's a couple of interesting labels on here. It says, what does it say? After opening the key switch, one should observe the water level. Well, fair enough. And it cannot be used until the water flow is heard or seen in 30 seconds. Otherwise, it will cause the machine to burn or scrapped, which is probably what's happened to this in its past life. But anyway, let's have a look at another label on the top here, and then we'll open this thing up and see what's inside. So we have another label on top here that says, warning, use the device before, please add pure water. And then it's got this really odd sentence underneath, cannot join mineral water, doing so may cause equipment damage. I assume this to mean if you put ordinary tap water in this, it'll destroy them, and that's a known thing, and I've come across this before. I like this line on the end though, it says, therefore equipment damage peril, and the company has nothing to do. So yeah, pretty interesting. Obviously this thing is built down to a price. Let's crack the lid on this and have a look and see what's inside. I've cracked the lid on this thing, and before I even get into what might be possibly wrong with the electronics, what I'm seeing here is really quite odd. I've never seen a piece of equipment built like this before. So let's take a close look and see what I'm talking about. So right down at the bottom here is what I'm seeing. This entire case, all of it, is made out of single flat pieces of plastic that have all been glued together. Like, seriously, I kid you not. This is a plastic strip that's been glued to the base. This is a plastic strip that's been glued up the side. There's little bits of plastic glued inside to join the corners together. It's the same up the top of the case. This is absolutely wild. Even the water tank is assembled out of flat plastic pieces. I don't know what kind of sweatshop this was assembled in, but by God, I've never seen anything so labor intensive when it comes to building a case before for what is allegedly a professional piece of kit. I'm just taking a look at the electronics assembly here, and yeah, there's a couple of things of note. There appears to be water damage all over the boards. So this little daughter board at the back that's connected to the main board is quite seriously corroded. There's corrosion at the top of the main board as well. This is the high voltage side, so these leads here go off to the capacitor and off to what would have been the laser head. When I actually received this piece of equipment, the end of the umbilical's actually been cut, so there was no laser with it. It was just a power supply and bare leads and bare hoses at the end. But yeah, just in amongst all of the bits and pieces there is water damage on the board as well. So I think what I should probably do shortly is actually take this board out and see if we can get a better view. To the right of it here, we have energy storage capacitor. This is probably around about 100 microfarads at 1,000 volts or so, something of that ilk. More or less, that's all that's in it. There is a controller behind the front panel LCD, but it's nothing exciting. It actually turns out that the electronics here are mounted onto a piece of plastic that forms one side of the water tank. And the water tank, like everything else in this, is made out of flat pieces of plastic that have all been glued or screwed together. This is absolutely unbelievable. I'm surprised that this thing hasn't gushed water all over the place, and in fact, perhaps that's why it's ended up in my hands. And we've got even more tales of woe at the back here. This is the IEC main socket, and we've got the neutral soldered onto this side, live soldered onto the other side. No heat shrink tubing covering these at all, and there should be, so highly unsafe, and there's no ground pin. Not one portion of this equipment is grounded at all. This is absolutely terrifying. This is an electrocution hazard just waiting to kill someone, it has to be said. You know, we've got a water tank in here that's assembled out of flat pieces, which is very likely to leak. It clearly has leaked at some point, right? We've got high voltage electronics very, very near the water supply, and the whole thing isn't grounded. It's made out of flat bits of plastic. Absolutely unbelievable. I thought I'd quickly hook this thing up to the mains and give it a quick blip to see if I can figure out where the magic smoke was escaping from. And yeah, this thing is absolutely wild. Keep an eye on the IEC socket at the back when I turn the switch. Yeah, did you see the flash? It turns out that whoever's manufactured the IEC socket has done a half-assed job of putting it together as well, and it turns out that the connections clearly aren't welded or soldered or whatever, and we've got sparks. Look at that. That's absolutely nuts. So looking at the back of the front panel here, and the horror show continues. In the middle there is a piece of metal. This is actually the rear of the key switch. The key switch is on the live side of the main circuit, which means that if the key switch was to fail internally, conceivably the key could become live and electrocute the operator. Big Clive would have an absolute field day with a piece of equipment like this. As for the rest of it, you'll remember I said earlier that I thought that this case was molded, and it actually turns out it isn't. Very much like the base of the case, this is actually assembled out of tiny little bits of plastic that have all been painstakingly glued together. This must have been an extremely labor-intensive job. At this stage, I'm sort of wondering what to even do about this thing. I mean, is it worth taking the boards out and cleaning everything up and seeing if we can get some life out of it? I mean, the board might be good, but crikey, if the rest of this is to go by, I mean, it's probably going to be pretty dangerous stuff. I'll pull the board out anyway, and we'll take a look and see if we can figure out what actually went wrong with this piece of kit. So I've got the board out now, and it's really quite ill. Down at the bottom here is a 1/2 ohm 1 watt resistor, which is missing its coating and now reads somewhere in the region of about a K or so. There's another resistor down in the middle of the power supply here that's also missing its coating. I have no idea what its value should have been. There's nothing on the silk screen down there. We've got a MOSFET here, which is short circuit across all pins. So it looks like that's well and truly destroyed. We've got a capacitor at the top here that looks to be part of the trigger circuit, and it itself seems to be short circuit as well. So I think the thing to do, I mean, this is kind of terrible, but just out of curiosity, I'll desolder these parts and measure them. The rest of the board looks pretty ill as well. I mean, there's significant water damage in here. It's evident that water's spilled on it at some point, and has caused it to eat itself. So I have the power supply apart here so we can do an autopsy on it. I've actually removed the daughter board here. It's covered in mineralization or corrosion or something. It's evidently been water damaged. I'm going to actually attempt to clean this off with some isopropyl alcohol and see if it's good. As for the rest of it, the main MOSFET was blown. So here it is. This is a W8 NB100. We've got a couple of resistors here which have gone open circuit. They've now basically become fuses. And then I have the SCR for the trigger circuit was also blown as well. This is also short circuit. This is a CR25AM manufactured by Mitsubishi, and I couldn't actually find a datasheet online for this, although I have got what I believe to be a modern equivalent. I've ordered some new components in. As a replacement for the SCR, I've picked this. This is a TYN1225 rated 1200 volts and 25 amps, so that should be just fine, I suspect, for driving the trigger transformer. The MOSFET, I found a like-for-like replacement for that, and I've got a couple of power resistors here to replace the ones that are blown. So let's solder all this stuff back together. I put together a diagram here to aid in debugging this switch mode power supply. What I was really interested in was how the trigger circuit works, to be honest. But yeah, I've got 3 discrete parts on here, so I'll just go through them. The top left here, I've got a pin out for the front panel, which is going to be very, very useful. And we can see that it just takes power and ground, and that's pretty much it. And then we've got a couple of signals coming out. So we've got a signal here that goes off to the switch mode power supply, which I assume to be like PWM control or something to change the output voltage. We've got a sense line, which is connected to some, what is it, a 1 meg resistor over here to the high tension line. So presumably it's sensing the amount of voltage available for the lamp. And then we've got a trigger out. The trigger out goes over here and is fed through this NPN transistor, which triggers a SCR, which dumps a high voltage charge from this capacitor through a trigger transformer here. Trigger transformer is pretty interesting. This is a standard switch mode power supply core, and what they have is a single secondary on there of about 100 turns of thick copper wire, and then wound over the top of that is 3 turns of copper wire as the primary, which is kind of odd. The inductance of this is some 200 millihenries on the secondary side, which is very, very large for a pulse forming network. But when the main capacitor fires through the flash lamp, the currents through here will be huge. They'll be so huge that they'll saturate the core, and that will cause the inductance to fall off really quite rapidly. So yeah, pretty interesting trigger circuit. I actually quite like it, and it's something that I'll perhaps replicate with some of my own designs, so pretty cool. The switch mode power supply itself, it's a dead straightforward switch mode power supply. We've got a transformer down here. We've got two secondary windings that are wired together in series, which will probably give us somewhere between like 500 and 900 volts out. They're rectified by a couple of UF5408s as the HT, and that's pretty much it. So I have the power supply largely reassembled here. I've got it topped up with water and I have it hooked up to the laser head, so we'll give it a quick test and see if anything explodes. I've got the camera looking into the back of the case so that if anything spectacular does happen, like the power supply is beyond repair and it disassembles itself, then at least we've got something interesting to look at. So we'll power it on and cross our fingers and see what happens. And so far so good, the pump and the fan are running. The question is, will the high voltage survive? So put it into ready and we'll go. Oh, interesting. It looks like we've got a winner. Right, nothing's on fire. I can smell a bit of something cooking though. So this thing doesn't appear to have caught fire yet. There's still chance, but we'll give it a go. We'll power this thing back up. I want to show you what happens on the front panel. So what I've done here is, I've already mentioned this, that the key switch actually isn't grounded, so I've wrapped this with very, very thick electrical tape. I don't trust this at all. I'm suitably terrified of turning the thing on, but we'll give it a go anyway. So we'll turn the emergency switch off and we'll turn this on. Now it goes through a little startup cycle, presumably to make you wait so that water circulating through the laser. And then we're done. We can do some stuff on the front panel here, set energy and so on, but I'll put it into ready mode. And if I press the fire button, it fires. And it definitely is firing the laser. Absolutely fantastic. Let me show you what the laser setup looks like. So here's the old tattoo laser head mounted on the bench. We've seen this before and we've seen it being driven by the power supply in the background there. I've plumbed this thing in to the tattoo laser power supply with a couple of bits of silicone hose, and the power feed goes off to the power supply as well. In front of the laser I have mounted a graphite block. This is my beam stop, and it's to prevent the beam from wandering off into the lab and doing any damage to anything that I don't intend to damage. Speaking of damage, before I even powered on this power supply, I did put on the all-important laser safety glasses. Yeah, there's no second chances with lasers like this. I think I mentioned earlier on in the video that when I received this power supply, the umbilical had actually been cut, so it was just bare ends. There was a couple of wires poking out and a couple of silicone tubes. So what I've done is built an enclosure here just to properly terminate these things. So I've got a couple of high voltage terminals on top for the flash lamp, and then I've got a couple of nipples on the bottom here so I can hook up the water supply. I think, you know, if I'm going to do anything at all with this power supply, it's going to have a complete rebuild, and I'll probably do something a lot more sensible than this, but it should work for now. Ordinarily, these tattoo lasers come with a foot switch so that the operator can turn the laser on and off. This didn't actually come with a switch at all, so again, I've created one. It's a nice little red push button that I can use to fire the laser. So now that we've seen the basic laser setup, before we start lasing things, we better take a look at the interface for this. I'll just turn this thing on. As before, it'll make you wait when it starts up, presumably to make sure that water's circulating. So there's just a couple of controls on here. We've got energy, so we can change the energy of the system. Presumably this just changes the high voltage. That's it. We've got frequency, which we can set to 1 Hz, 2 Hz, 3 Hz, 4 Hz, and then 5 Hz. So the maximum repetition rate is 5 times a second. And then we've got status, a function button down at the bottom here. And if we press function, oh look, it's a little disco. If we that's kind of irritating, the flashing different colors. If I press the function button, it'll go from standby to ready. And if I press the fire button, we fire once and the counter increments. So we've got a nice little counter that says how many shots we had. I know that everybody who visits this channel wants to see lasers do some stuff, so let's point the camera towards the laser and see it do things. You'll notice that the view through the camera looks filtered. This is because the camera is wearing laser safety glasses to protect it. The light emitted by these lasers is very, very intense and can easily damage CCDs. It can easily damage your eyes as well, so I'm also wearing the all-important laser safety glasses. Anyway, let's get this thing fired up and see what it can do. Nice. So it turns out there actually still is a fault with the power supply. I've not quite worked out what this is, but let's see this anyway. The laser will fire, so I'll turn it on and we'll fire it. But then after it fires, for some odd reason, it seems to strike the tube, which is quite strange. So we'll turn it on anyway. There we are. So we'll hit function and fire. Nice. Okay, so that's just fine. And the tube struck. Interesting. So I got 2 shots out of this, and then the tube actually strikes an arc, which is very, very interesting. Let's move the camera around and we can see what I mean. So there is still a very serious fault with this power supply. What we've got here is a view of the end of the head, and we can see the end of the flash lamp just poking out there. What should happen is when this laser fires, we should get a single bright flash out of the end of the quartz envelope for the flash lamp, and that should be it. There shouldn't be any more light being emitted. But what's actually happening is we get to fire it a couple of times, and then it seems to strike an arc inside the flash lamp itself, which is definitely not good for the flash lamp. It'll cook the flash lamp to the point where the whole thing explodes. So let's see that actually happen. Hopefully I can do this without the thing eating itself, but I'll turn the power supply on and we'll have a look. So we'll fire the laser. So there's a single flash, and that's exactly what we expect. We'll fire it again, and now it's glowing. Yeah, so I've just turned the power supply right off before it does any damage. So yes, it is in fact striking an arc inside the tube. This is probably what caused the power supply to fail. So yeah, there's something very, very seriously wrong still with the power supply, and certainly don't want to destroy this laser head. So yeah, this thing works insofar as it doesn't explode when you turn it on, and it will actually cause the laser to fire. But beyond that, it's causing arcing in the flash lamp, which is definitely not good for the laser. If it's left to continue, it will melt the flash lamp. The flash lamp will probably explode. It'll probably destroy the power supply while it's at it. And so yeah, this is very bad. The only reason I can think of that an arc would be struck inside the flash lamp is if the voltage from this is too high. So we must be looking somewhere in the region of about 1.5 to 2,000 volts in order to cause that to occur. So the switch mode power supply is out of regulation. It's no longer being regulated, so it's just being let to run and charge the capacitor up as high as it wants. The actual regulation takes place oddly on the front panel. The front panel's got a microcontroller on here, an 89C52RC, and it is responsible for sending signals back to the switch mode power supply, instructing it when to turn on and off. So there's obviously a problem with the front panel. So in order to fix this, we'd have to strip out the front panel and reverse engineer that. I'm not really too keen on learning how to program the microcontroller in this. So yeah, I suppose ultimately I've got 2 choices. I mean, we've already seen that this thing is it's a death trap. It's a widow maker, right? I'm surprised that no one has been killed by one of these. The whole thing has been built down to a price. The entire case is manufactured out of little bits of plastic, all arrowdited together. The water tank is made out of bits of plastic, arrowdited together. On the side of the water tank, we've got a switch mode power supply that's obviously had water spilt on it when it's been filled. If it doesn't get water spilled directly on it, it's going to suffer from condensation being on the side of a tank, and the thing isn't conformally coated. There's no earth. Sparks fly when you power it on. Potentially metal parts, because it's not grounded, could become live. So yeah, this is an absolute horror show. So I'm going to stop working on it in the condition it's in, and that leaves me with 2 options. Either I can strip out all of this stuff and build it into a proper metal case and do a proper job, which is a possibility. I mean, we can always regulate the switch mode power supply with a shunt regulator, right? We could use that as feedback. We could use a little voltage divider, a TL431, and feedback into the power supply, and we're all done. Little variable resistor, little voltage meter, and we'd be hunky-dory. Had to figure out some way of triggering it, but maybe we can get like 10 hertz out of the laser, which would be really quite nice to see. The second option is, of course, just gut it, use it for parts, and build something else. leave a comment down below. This isn't going to happen this week or this month because honestly I want the bench space for another upcoming project. But sure, I can gut this thing out and we can make a decision. Either let's put it in a metal case and see what it can do, or we'll just strip all the bits out and use it for another power supply. If you want to see more videos like this, don't forget to hit like and subscribe so you don't miss new content. As always, a huge thank you to my Patreons, channel donators and subscribers. Your support makes science and engineering videos like this possible.